Hello everyone. In this video, I'm going to go through an exam question and show you how to answer this question without spending too much time and at the same time get full marks. This is a two-part question. First part is asking us to prove that the depth of neutral axis is approximately 215 millimeters, which is this value, a depth from this topmost fiber to this neutral axis, which is x. And the second part is asking us to calculate the moment of resistance of this reinforced concrete section. Second part is relatively easy to solve once we complete the part 1. If you would like to take more time and understand this question, you could pause the video and take a look at what we have here. We will be using the rectangular stress block to solve this problem. You have seen this before and I will come back to these diagrams shortly. Now let's write down the values which are not given in the question. Fyk is equal to 500 megapascals. Fyk is the characteristic yield strength of reinforcement. Es is equal to 200 gigapascals. Es is the design value of the modulus of elasticity of reinforcing steel. Alpha cc is equal to 0.85. Alpha cc is the coefficient taking account of long-term effects on the compressive strength and of unfavorable effects resulting from the way the load is applied, and this is related to concrete. Then we have our partial safety factors. For concrete, gamma c is equal to 1.5, and for steel, gamma s is equal to 1.15. Going back to the forces and stress block diagram, this lambda is 0.84 FCK below 50 megapascals. You can see that we are given that the concrete grade is C2530, so it is below 50 megapascals. Lambda is equal to 0.8. Then this eta is going to be 1 because our concrete grade is below 50 megapascals. Eta is equal to 1. Lambda is the effective height of compression zone factor and eta is the effective strength factor. And then we have epsilon Cu3, the ultimate compressive strain in the concrete. Epsilon Cu3 is equal to 0.0035. Let's begin the calculations with calculating the design strength values of concrete and reinforcement, starting with FCD. FCD is equal to alpha cc times FCK over gamma c. Alpha cc is 0.85, FCK is given as 25, and gamma c is 1.5. This comes to 14.167 megapascals. Then we can calculate the design yield strength of reinforcement. Fyd is equal to Fyk over gamma s, which is equal to 500 over 1.15, and that's equal to 434.78 megapascals. Then we can calculate the yield strain of reinforcement. We will need this value towards to the end of these calculations to prove that the reinforcement is yielding. So the yield strain in reinforcement is epsilon s yield is equal to Fyd over Es, that is equal to 434.78 0.78 over 200 gigapascals. This is equal to 0.00217. Next step is to calculate the area of tensile reinforcement. We have three number 32 mm diameter bars. Cross-sectional area of reinforcement AS is equal to 3 times 5 times 32 over 2 square. This is equal to 24,013 square millimeters. Now let's move on to calculating the forces in concrete, which is this FC value. First we need to determine the effective height of compression zone, which is this height from this point to this point. That is basically lambda x. In the question we are given that x is equal to 215 in here. Therefore lambda times x is equal to 0.8 times 215, that is equal to 172 millimeters. It is quite clear that the compression zone extends beyond the depth of flange, because the effective height is 172 millimeters and the height of flange is 140. Therefore, the FC is composed of two forces: compressive force in the flange in this area and compressive force in the web. Let's call these F1 and F2. F1 in here and F2. We can draw the same forces here as well, F1 and F2. This should be F2. And the depths to these forces from the topmost fiber here are A1 and A2 respectively. So this would be A1 and this would be A2. Same here, this would be A1 and this would be A2. By inspection we can say that A1 is half of 140 because it is the centroid of compression zone within this flange. A1 is equal to HF over 2, which is 140 over 2 is equal to 70 millimeters. Then we can write A2 is equal to H flange plus lambda x minus H flange over 2, and this is equal to 156 millimeters. Now let's calculate FC1 and FC2. FC1 is equal to FCD times BF times HF. BF is the width of the flange and HF is the depth of the flange. This is equal to 14.167 times 460 times 140. This is equal to 912 kilonewton. FC2 is equal to FCD times BW times lambda x minus HF. BW is the width of the web. This is equal to 14.167 times 300 times 172 minus 140. This is equal to 136 kilonewton. Now we can add FC1 and FC2 to calculate FC. FC is equal to FC1 plus FC2, which is equal to 912 plus 136. This is equal to 1048 kilonewton. Now let's check whether the reinforcement is yielding. Let's check the strain in the reinforcement, which is epsilon s, and that is equal to effective depth d minus x over x times epsilon cu3. For our concrete section in the question, d is given as 450. This is equal to 450 minus 215 over 215 times 0.0035, and this comes to 0.0038. Previously we calculated the yield strain in reinforcement as this value 0.00217, so it is clear that this reinforcement is yielding because this is bigger than 0.00217. Now we can calculate the force in reinforcement, which is Fs. Fs is this value. Fs is equal to Fyd times area of reinforcement. This is equal to 434.78 times 2413, and this comes to 1049 kilonewton. We have calculated Fc as 1048 kilonewton and Fs as 1049 kilonewton. That means Fc is approximately equal to Fs. This is the proof that the internal forces are in equilibrium. Therefore, the given depth to the neutral axis x value, which is 250 millimeters, is correct. Now we have completed part 1 and we can move on to part 2. For the second part, we can take moments about topmost fiber and calculate the moment of resistance. MRD is equal to Fs times d, which is effective depth, minus Fc1 times A1 minus Fc2 times A2. And if you plug in the numbers and calculate this value, MRD comes to 387 kilonewton meter. And we have completed both parts of the question. If you have any questions regarding this video, please post your questions in the comment section. If you like the video, please like the video, and if you would like to see more videos like this one, please subscribe to our channel. Thank you for watching the video.